Okay, there we go. Excellent, Peter. Yeah, you're absolutely right that um, this was part of my undergraduate senior thesis at the University of Vermont, where we were working out in the Mojave Desert, and we were studying how these things right here. I can, yeah, circle it. Yeah, these things right here, army tanks, how those influence the hydrology and essentially the geomorphology of desert surfaces. And so we had several sites where we would go out and we would develop a method for measuring a rate. Now, Peter said infiltration, or no, he said percolation, but there's another term I introduced is infiltration. Does anyone remember the difference between infiltration and percolation?
Is infiltration that's going into the ground and then percolation is moving through the ground?
Excellent. Yes, Brandon's absolutely right. Infiltration, remember it, infiltration starts with in. And so that's the water moving into the ground. And then once it's in the subsurface, that water moving in the subsurface, we call percolation. And so those rates can be different. And so a rate of infiltration or percolation is going to be in length per time. So we talk about a surface as being able to infiltrate in centimeters per hour or inches per day. And so these experiments we set up here was essentially we get a test plot and we would buy some of this metal flashing right here. So all this is stuff you buy at a hardware store. Has anyone ever had to re-roof their house before? No? Yeah. This is the stuff you put it basically around the chimney where you're making that connection between the asphalt tiles and whatever else is sticking out of your roof. So we just took some metal flashing and we would dig out the basically the downstream end of this, and we would use a plaster of Paris. You can't see it, it's under the duct tape here, but under the duct tape, there would be basically a plaster of Paris, which is our little channel, and we would just harden it so that it wouldn't erode away. And then we could collect and measure the water that was running off our test plot. These little orange things here, those are our rain gauges. And so you saw pictures, see if I can go back. Oh, I forgot where the picture is, sorry. Of the backpack sprayer spraying on these. So here it is right here. Here's the sprayer, and we're raining on this. We can measure how much rain in our rain gauges. And what we do is we measure the amount of precipitation we put on the plot, and then we measure what runs off. And the difference between those is going to be our amount that soaks into the ground and is infiltrated into the ground. And that is how we calculate our infiltration rate. And so there's Ari Matmon right there, who's switching out the buckets for me. And Ari was a postdoc at the University of Vermont at the time. And he's now a professor at Hebrew University in Israel. And so he's an excellent world-class geomorphologist. Probably some of the best desert geomorphologists in the world are in Israel. They have some of the best desert geomorphology programs, and that's due to the fact that Israel is a very dry place. So they're very much interested in dryland processes. So here you can kind of see on the left, our picture here, there's the water that's pooling on the surface and running off the surface. And so we would run these plots in different locations, places where there were active tanks and places where there were not active tanks. And then we would see how the compaction changed the infiltration rates. So it was part of a larger study where we were looking at other things as well, but this was the geomorphic hydrology part of it. And so we were able to show that, you know, where you have these tanks, they absolutely decrease infiltration rates, just like places like this. So here we see a similar place. What's going on here? Does anyone remember from the lecture what's happening in this picture?
College students parking on the grass because there's not enough space for all of their cars, and you're just compacting the soil and the grass And so you
Excellent.
can't get water into the ground.
Excellent, Carmen. You're absolutely right. This is from the University of Vermont. And UVM, like many college towns, suffers from a housing problem where most juniors and seniors live off campus. And what happens is you have these old single family homes, these beautiful big single family homes that generally would have had one car, and then they're sold, and then a slumlord buys it. And you go from having one family there with one or two cars to maybe 10, maybe 11 students there, each with their own car, and there's not enough parking, so they end up on the lawns. And this is a huge problem, because all of a sudden, when you get runoff, you have more runoff than the engineers expect, and so the drainage system cannot handle all the excess runoff. And so what happens is it just runs off the street. And in this case, in Burlington, all that excess runoff just goes straight down into the lake. And so that causes water quality problems in Lake Champlain. So geomorphic hydrology has very, very much real world applications. So yeah, okay, cool. Good work, everyone. Let's then stop the share here. I want to go over the recurrence interval and calculating the probability. You guys read it in the textbook and saw me lecture on it a little bit. Is everyone, how many people have already calculated kind of recurrence intervals before for another class or something? Give me a thumbs up. So maybe one or two of you have. How many of you feel completely comfortable with this and are just ready to go, and I should just shut up and let you hop into the lab? Not everyone. Okay, good. So what I'd like to do is just take a really simple example of how we calculate these. I'll do it by hand, but you'll just be using Excel to code in actual equations into Excel. And I am, to a certain degree, kind of assuming that you've worked a little bit with Excel and know how to use the equation function, the equals in Excel. If this is completely foreign to you, I can hop into your breakout room and share screens and help you learn how to navigate the world of Excel. Okay, so let's go ahead and work on these two features on the whiteboard. No, the real whiteboard. Video. Oop, I stopped my video. Okay, is everyone looking at the whiteboard now? Yes? Okay. I'm going to move this up to a different screen so I can see it as well. So, all right, I am a little bit away from my microphone. Give me a thumbs up if audio is okay. Okay, thanks, Al. Great. So, what I want to start with is essentially just the equations that were presented. A recurrence interval, and it doesn't matter what we're talking about. We can be talking about any values. It's just this statistical determination. So you could be talking about how often a flood occurs, how often a certain size rainfall event happens, how often a tornado blasts through Missouri. Doesn't matter. It's just a statistical determination that's going to tell us how likely an event is. And you're actually going to see that our calculation of the recurrence interval is independent of the data of our actual data sets. Okay? Okay, so our recurrence interval is equal to n plus 1 over r. Actually, let me do this how I think it's probably in your slides, lowercase r. Can someone remind me what n is here?
The number of observations.
Excellent, Brandon, yes. N equals number of observations. Okay. So that's our simplest determination of this, of the likelihood of an event occurring. We can flip that. That's going to be a recurrence interval, how likely it is to happen. Now, what those numbers mean depends on what you're talking about, right? If we're talking about yearly data sets, then our recurrence intervals are going to be in years. But if you're doing something with weekly data sets or daily data sets, then your units would be in days or weeks. So does that make sense? It kind of depends what you're analyzing, what that recurrence interval represents. We can also just simply call it also the probability of a given event occurring. How likely is an event to occur? We just call this the probability, P, and that's going to be equal to, very easy here, 1 over our recurrence interval. Okay, so those are our equations right there, not too complicated. Let's throw in some data. Let's say that we've got how much it rains, and we moved to a new place and we set up a rain gauge, and we're going to calculate the total amount of rain every year. Okay, and so we'll call that yearly rainfall. Let's say year 1, the first year we're there, it rains during the course of the year 15.2 inches. Year 2, it rains 10.1 inches. And then in year 3, it rains, let's say, 16.3 inches. Okay? Let's say after 3 years, we want to actually now create our recurrence interval, estimate our recurrence intervals. Another way to think about this would be a probability, or another term I use is exceedance probability. And how likely is it that you're going to exceed these values? That's why we call it exceedance values. You'll often see that when referring to flooding is exceedance probability. Okay, so what do you guys think? What's the first thing, if I'm going to calculate the recurrence interval, what's the first thing I have to do with these numbers?
Find their average.
We can find the average, and so you guys know how to find averages. We could find the average, but if we're just going to start throwing this into our equation here, we don't necessarily need the average just to calculate the recurrence interval. If I threw these numbers at you, what's something we would need to do to this data set so that we can start manipulating it?
You could rank them.
Yeah, we need to get these, we need to rank these in some sort of order. And so depending on how you're doing this, often you rank them with the largest value as number 1, and then your other values rank increasing numbers from there. So what's our largest number in our data set?
16.3.
16.3. Okay, so we'll call this, you guys can't see that probably, sorry. Rainfall. $16.3, and we're going to rank that. And that gets to be number 1. Yay, number 1. Woohoo! All right. Our next number then is going to be, write these a little bit bigger for you, 15.2. And that's going to be rank number 2. And then our final here is 10.3, and that's rank number 3. Okay, so now we've got our rank right here. Does everyone see that? We've got a rank, and so now we can start to use this equation. Let's, for simplicity, let's just write this out. Let's calculate our n plus 1 for the data set and write that on our chart as well. So what is n plus 1? What's that value for our first number? Anyone want to be brave? What is our n plus 1?
Is it 4?
It is absolutely 4. We have number of observations, 1, 2, 3. We have 3 observations, so 3 plus 1 is math even I can do, and that's 4. What's our n plus 1 for the second number? Oh, sorry, hold on. Okay, we're back. Does our n plus 1 change? No, I see people shaking their head no. Okay. So now we can calculate our recurrence interval. So in our first case here, we've got our 4. So our n plus 1 is 4, and our rank is 1. Someone help me out with the math here. What's 4 divided by 1? There we go. Thank you, Zachary. 4. All right. So our recurrence interval is 4. So what that means is that since these are yearly rainfall values, we expect every 4 years to get a rainfall amount of 16.3 inches. Let's do the next one here. N plus 1 is 4 divided by 2. Can someone help me with the math on that? Ah, nice. I like the fingers. Thank you. 2. That means that roughly every other year, we would expect to get at least 15.2 inches of rain. And then our last one here, 4 divided by 3. Does anyone have the math on that for me?
1.3 repeating.
1.3 repeating. So let's keep this in sig figs here. Basically, if we're reporting our values in tenths of an inch, we've got one significant figure, so we'll call it 1.3. So 1.3. Which I should mention that significant figures are very important in geomorphology. I don't like it if I ask you to calculate an erosion rate and you calculate it all the way out to 15 digits, right? Do we really know the erosion rate down to 1.8892446 meters per year? No. So we should take care to pay attention to our sig figures. That's an important part of science. Okay, good. All right, so I think we've got just enough room over here. We can calculate our probability as well, which is just 1 over our recurrence interval. So what is our probability for the first number? Anyone want to be brave?
Is it 0.3? Because rounding up the 0.25 to 1 sig fig?
Yeah, so if we're rounding up, it would be 0.3. 3, just for the math sake, for people that are thinking about the math, just of this, it's 0.25, or another way of thinking about that is 25%. But you're right, we would round up on that, but I don't want people to get confused of what it is, because all we did was we took 1 and divided it by 4. Okay. So what's our probability then of a 15.2?
Half.
Half, right? About 50%. Whoa. Now you guys can't quite see the percents over there. I'm just writing it in percent. And then our final one is 75%. So how you can read these is you have a 75% chance of it raining at least 10.3 inches in any given year. You have a 25% chance of it raining 16.3 inches in any given year. So once you have these numbers calculated, then you can actually plot them on a graph. So notice here, we didn't actually use any of our actual values to calculate this recurrence interval, right? It's just based on the number of observations and ranking them. How we actually plot this with our data is now we put the yearly rainfall in inches. And we put our recurrence interval on the x-axis. Sorry, is this a little hard to read? I'm going to get rid of our axis label for a second. 5, 10, 15, 20. And so now we can plot each of our data points here. So our first one here, our recurrence interval of 1.3, that's right here around 1. And we have a rainfall amount of about 10 inches. So that would be the first point. Our second point here at roughly 15, that has a recurrence interval of 2. So I can go up to 2 right there. And then finally, our next one,
we can't see the x-axis of the graph.
What?
We can't see the x-axis of the graph.
Darn it. There we go. Sorry about that. So we've got a recurrence interval. I put on my recurrence interval of 0.1, 1, 2, 10, 50, 10, 100. I'm going to talk about that scale here in a second. I'm just plotting on there right now. And our last one is 16.3. And that has a recurrence interval of 4. Okay. So once you plot your data, then it's really fun. Then you just get to make a best fit line using a ruler. Where's my ruler? Hold on a sec. Where'd it go? Sorry about that. It was in the other room. Okay, back with my ruler. You plot a best fit line through your points. And you're off to the races. So now if we want to estimate the recurrence interval of a 100-year event, basically an incredibly wet year, we can just read up to our line and over to our y-axis. Everyone noticed that I had a bit of a weird scale down here. What type of scale is this? How did I arrange these numbers? What do we call this?
Log scale.
Yeah, this is a log scale. And so essentially on a log scale, your axis is you're going to have the same amount of space by orders of magnitude. So this is roughly right that if, see my fingers here, from 0.1 to 1, it takes about this much space. And then from 1 to 10, it should take about the same amount of space. And then from 10 to 100, it should take the same amount. So that's a log scale, a logarithmic scale. And when we plot our exceedance probabilities, if you have a normal distribution of data, your line is going to fit a straight line on a log scale like this. Now, I'm going to give you the opportunity, those of you that get real into this and excited by this, how we can mathematically model this line using different distributions. And in the Excel spreadsheet, I give you a link to a way that you can plot what's called the Gumbel distribution. And the Gumbel distribution is an assumed probability distribution based on the shape of your data. And so that part's just extra credit. The lab itself, you're just going to be plotting these, your recurrence intervals, and then making a best fit line, just drawing it on yourself with a straight line. So that's pretty much it. That's how we make these. They sometimes confuse your brain how things are worded, right? Going between probability. And so again, with a recurrence interval, it's how likely we expect an event to happen. And so this is rainfall. So what this means is that we expect that every year it rains at least 10 inches, right? And that has a probability of roughly 75% of happening if we're at 1.3. Okay. So you guys kind of have used these numbers before. I mentioned it in my lecture for today as well. Why might you be careful right now about making the estimate of the 100-year, the maximum amount of rain in 100 years? Why might that be problematic based on this data set?
You don't have a lot of data points.
Yeah, I don't have a lot of data points. And so maybe because on my graph, it's a log plot, it looks like, hey, we're kind of close, up there and to events we've observed, but that's very misleading on this log scale, right? We've only observed, if you're trying to make an estimate of the 100-year flood, we've only observed 3% of the record. And so that can be pretty darn problematic, making that estimate out to the 100-year. So what do we call it when we're making an estimate outside of our data range? What's that called?
Extrapolation.
Thank you. Was that Maggie?
Yes.
Yes, we call that extrapolation. What do we call it when, if I want to plot and I want to get the recurrence interval of a 1.8 or something year event, and I read over to the line, and then I read off to the graphic? What do we call that type of estimate? Not extrapolation, when you're estimating within your known data set range.
Interpolation.
Excellent. This is an interpolation. So extrapolation beyond the data range, interpolation within the data range. Which one's more safe? Interpolation. You want to interpolate, but oftentimes you have to extrapolate. And oftentimes a place where you'll see these recurrence intervals is with floods, right? We're always interested in this 100-year event for flooding. And actually that 100-year event is really important because we use that. That's a measure we use for determining essentially if someone is in a floodplain or not. And it kind of varies the type of insurance, housing insurance you have to buy when you when you get a mortgage for a house. And so that's the 100-year event is required basically for all rivers in the country so that we can determine properties within that 100-year value of what's going to get inundated in a flood. And so for that reason, you might have a river and you only have 20 years of data. You've been gauging it for 20 years, but we have to make that estimate of the 100-year flood based on 20 years of data. And 20 would be better than 3 in this case. Okay, so I agree with you that, yeah, this is one reason to be hesitant with this number is because we don't have a lot of data points. Based on the lecture or your gut feeling about this maybe, what's another reason to be critical of your estimate besides just extrapolation?
You're basing a lot of this on events that happened in the past, and like you don't know what's going to happen in the future. And along with climate change, you could really end up in like a really bad place if you extrapolated data.
Yeah, Carmen's right. And Carmen said we're basing a lot of this on the past. I'm going to one up Carmen here. I'm going to say we're basing all of this, not just a lot, all of it on the past. And what we're doing is we're making an assumption that the past is a predictor of the future. And sometimes that's a pretty darn good assumption, but when it's a pretty crummy assumption, oftentimes is associated with events changing because of climate change. And so that's another reason too. And that's the idea of shifting baselines, that we assume a statistical distribution that stays constant in time. But if that statistical distribution is moving, then this becomes an even dicier exercise. So excellent. Yeah, I completely agree with you that that the future might, the past might not represent the future. And along with that, even if you don't have climate change, remember this is purely a statistical determination. It's base statistics. Can you have, is it possible that 2 years in a row, you have values where it rains 15 inches? Or 25 inches? Sure, nature does what it wants to do, right? We're trying to fit statistical models to describe how nature works. But again, just because you've had one event, a large size, doesn't mean you're safe. Every year has the same probability. And that simple fact is the reason why Las Vegas makes a lot of money and most everyone goes home from Vegas poorer than when they got there. It's because most people don't understand statistics, right? Does everyone know like the game roulette? So the game roulette, right? The wheel's spinning around, you put the ball in and it spins around, then it lands on a number and a color. And so, right, the color can either be black or red. There's 2 green ones, but let's forget about that. I know that the pure gamblers are annoyed, but let's just say on a roulette wheel that you've got black and red. And so it's got a 50-50 chance, right, of landing on a red one, the ball every time. So let's say it's landed on a red, and then you go again and you do another spin of the roulette wheel and then it lands on red again. And then you spin the roulette wheel again and it lands on red again. What's the probability on the next spin that it's going to be red again? It's still 50%. And so that's, again, why Vegas makes money is people don't understand simple statistics. It's the same things with these flood frequencies that, that you can have unusual events, rare events happen right after another. And we saw that on, for example, just the Yellowstone River experienced a 100-year flood in 1996 and then again in 1997. So, okay. I don't know if I should come back over here first or stay up there. But does anyone have questions on that?
I have a quick question.
Yes.
Can you explain again why you're using the log scale?
So the log scale, without getting that's a really good question, Peter. I think was that Peter?
No, Henry.
Oh, sorry, Henry. I'm not looking at this at the pictures right now. Hold on one second and I can start looking at your pictures again. Where, I've lost my screen, sorry. Where are you guys? Okay, there it is. All right, so why did I use the log distribution? Essentially, without getting into too down the weeds of the statistics of it, we use that because we assume that our data in terms of the floods follows what's called a normal distribution. Another name for a normal distribution is a bell curve, right? So if I go back to the whiteboard, the virtual whiteboard this time, if we have, maybe I should just, if we have observations on the y-axis and the size of the event, magnitude on our x-axis, we assume that our data is shaped like a bell curve. And right in the middle would be our average. And if this is perfectly normal, that this both sides of the bell curve are the same, then the median and the average are the same. And so again, what we're, right, so this would be, you know, if this is rainfall event, we expect most years to be that average. Let's say in this case, it's 10 inches per year, but very rarely it's out here on the tail of 15 inches per year. And sometimes it's really, really dry. It might only be 8 inches per year. So we assume when we make these statistical determinations that our data fits this bell curve. And with that assumption, if our data fits this bell curve perfectly, and then on a log axis, our observation, our magnitude versus recurrence interval is a straight line on a log axis if this distribution is correct. The cool thing is you're playing around in Excel, and so in a heartbeat, you can switch. How do I get back? I'm lost. There's the controls. Stop share. In just a second, you can switch between a log scale axis and a linear axis in Excel. And so you can see how the data looks on log versus linear axes. So that again, without diving into the statistics, that's my best answer for you. Does that help at all? Okay, awesome. Other questions?
Yeah. I'm wondering if like the same statistical probabilities and like these equations that use for like 100-year floods, for example, could be applied to like droughts if you just like reverse the rankings from like lowest to highest in terms of like rainfall, or if they're like less predictable.
No, I mean, by predictable, all I can say is that this type of analysis works if your data are normally distributed. So if you have droughts that follow, and drought just is a rainfall, right? And so you're just looking at the other end of that tail of that distribution. And so instead of looking at the 100-year event, you can look at how likely you are to get the 0.1, and then it's essentially the same thing. And so you can either rank them backwards or just look at the other side of the distribution going below 1, if that makes sense. So yeah, you can say how likely is it that it rains less than 8 inches, which maybe we consider that drought. So what's the probability? Is it a 1% chance or a 0.1% chance that we're going to get rainfall less than 8 inches? So yes, these are used on the other side as well. Good question.
Okay, cool.
other questions? None right now? Do you want me to show you all really just real briefly how easy it is to flip the axes in Excel from linear to nonlinear or linear to log?
Yes, please.
All right, cool. Then I shall do that with some data. Okay, share. All right, you should be looking at an Excel spreadsheet now. Let's just start some new here. Okay, so we got some numbers. And on this side, we just need a second set of numbers. Actually, no, let's do this. So when we're making an XY graph in Excel, you go to Insert, Charts. Remember to never, ever be fooled by Excel. Resist the urge to insert a line chart. Those are for business majors only. Keep away from them. We want XY scatters. So we're going to do an XY scatter. Excel always thinks it's smarter than you and tries to plot your data for you. I always just delete it and say, don't do that. I want to choose my own data. I'm in charge of my own future, not you, Excel. Okay. So in chart design, I can select data, and I'm going to add a data set, and I'm going to select the X axis first. So let's say that this B column is our X axis. You could click and drag all the way down, and then hit return. Or if you're like me and you want a shortcut, you can click in where you are and you hold Shift and Control, and then you hit the down arrow, and it automatically selects everything in your column down to the next gap in data. And we can do the same for our Y-axis. Start at the top, Shift Control, hit down. We've got, whoa, where'd they both go? Yeah, okay, they're there. Okay. So there's our data. We actually have one negative value. Let's just get rid of that for now because, okay, so there's our data now plotted. Let's say that on the x-axis, you wanted your x-axis to have a logarithmic axis. You click on the axis, and then you click Format Axis, and then your axes options show up on the right here. So we could set things like where we want it to start and end. But what I want is to change it from a linear axis to a logarithmic axis, and we'll just do base 10. None of you base 8 nerds out there, I want base 10 for this, okay? We'll do base 10. And then now, the same amount of space on the x-axis is the same amount of space is covered by an order of magnitude from 1 to 10, 10 to 100, 100 to 1,000. It's so important in science, in all the sciences, to be able to think in orders of magnitude. Orders of magnitude are so important. So being able to jump quickly between an order of magnitude, multiply between them, visualize them is really key. So that's why one reason why you see a lot of log plots is because we're dealing in the sciences with really big or really small numbers or numbers over large scales. Okay. I remember a very famous prof in geomorphology. Frank Pizzalia, who's a prof at Lehigh University, did some seminal work looking at uplift and erosion in the Olympic Mountains on the Olympic Peninsula. Frank, I remember he was giving a talk once and someone asked him why he was plotting his data in log space, so a logarithmic axis on both the X and the Y axis. And he looked at it and he goes, I don't know. I think because it looks cleaner, it looks straighter. The lines look straighter. And of course, that's not the reason you should ever just use a log axis. There should be a reason why. And that's what I was trying to explain to you all, that in this case, the reason we're using a log axis is because we're assuming a normal bell curve distribution and plotting exceedance probabilities. So you don't want to use it just to hide like outliers in your data set, right? Because of that order of magnitude, if you have a couple of really big numbers, it's kind of easy to show that they're not so unusual, right? By throwing it on a log axis. So don't do that. That's called lying with statistics. Okay. Any other questions? I think we're all set then. Good. So basically, I'm going to throw you into your breakout rooms. And the lab, oh, let me, okay. One more thing, I'm sorry. You can find the lab on the Canvas. Week 3 page, there is now under Lab 3 Geomorphic Hydrology, there's the handout. And then there's going to be 3 files, okay? 3 files. You follow the lab handout, you get the data from the Excel file, but then you're gonna just make your own Excel, well, you can use that one, or you can just start a new one that you're basically doing all your work in, all your Excel work in. There's not an assignment link yet. I need to get the group set up first, and then we'll have that assignment. And then basically all you're going to turn in is one Excel file into the assignment for this lab. Does that sound good? One other thing to note, back in the olden days of last year, I would often have you guys, I would take all the average values from Kennewick and stick them in an envelope and have you randomly select numbers out of the envelope. And so that you can see how important it is to have a lot of observations and not a few observations. I am still trying to recreate that experience for you by using a random selector from the list, just like you're blindly reaching into the envelope and picking out a value. I tried to code it into Excel, but it was taking a long time to code a random selector in, but I found a tool on the internet. So check this out, bear with me. This might save you a little time. What you do is you download this Kennewick yearly precipitation file to your computer. So it's just the list of numbers as a .txt, a text file. So I'm just going to throw this in my downloads for right now. And then there's a link in the lab to this online random picker. And the cool thing about this is it allows you to enter numbers, and then it'll pick a random one for you. It's a way of randomizing it. Instead of making you type in all the numbers, you can just throw in that file, that .text file that I just threw in my downloads folder. There it is, Kennewick yearly precip. Look at that, and then it populates it for you. So now all those are the amount of rain in Kennewick every year. 1 year it rained 9.03 inches. Ooh, here is the wet year, 13.91. And so you just pick random item, and it randomizes for you. And then it spits out one of your values. Isn't that fun? So I think it's fun. So you can randomize it, and that allows us to simulate randomly choosing values out of the hat. Okay, that's it. Now I think I really am done.
How many random data points do we need?
It says it in the lab. So yeah, because you're going to be looking at different numbers. So yeah, you're going to be looking at different populations, how means and medians change based on the numbers that you pull out of the hat. You can find other ones too. If you can find another random picker you want online, or you can look at how to do it in Excel. Or if you really want, if you're getting bored of that, play with it once. But if you're getting a little bored, you could just close your eyes and just point at a number on the list and pick them that way too. The idea is just to randomize it. Good question, Carmen. Okay, I'm going to open up the breakout rooms. However, it might take me a second because I want to put you back in the groups from this morning because I don't want to overload you with different people you have to meet with.
Lyman, can I ask you a question?
Yes.
Would you recommend finishing that homework assignment or starting this lab?
It's up to you. I would recommend starting the lab since I'll be around and can help, but I could help with the homework too. Either one. I gave you this lab will be due next Wednesday. I gave you an extra couple days. I gave you all the way till next Friday for the homework assignment. I wanted, because I know that you've got your first check of your landform atlas, so I wanted to give you plenty of time to get stuff done. We'll use some time on Friday too to work on, give you some group time to work with your groups as well on Friday. So just keep in mind those deadlines when deciding what to work on as well. Great question, Maggie. Okay, so I have to manually put you guys in breakout rooms based on this morning. So let me see. Breakout room 1 is Carmen and Will. Breakout room 2 is Maggie and Zachary. Breakout room 3 is Ben and Mira. Breakout room 4 is Brandon and Henry. Breakout room 5 is Fielding and Peter, and breakout room 6 is Noah and Sharon. Okay, the rooms are open. The meeting will be open until 3:50. If I'm not there, just give me a second. Paul just finished his school day and he has his afternoon PE lesson, which is tennis, that I have to get him ready for. So I might be upstairs just getting him out the door, but I'm having a neighbor take him to that so that I can stay here with you guys. So I will be back, but if I'm not right in front of my computer, that's where I am. Okay. All right. Have fun in your breakout rooms. You can always pop out or invite me to join you and I can answer your questions. Thanks, everyone. Hey, Bob, how'd afternoon go? Did you stay positive? Yeah. I'm so happy. We need one to go to the party in my tummy. Okay, let's go. There's a party in my tummy. So yummy, so yummy. There's a party in my tummy. So yummy, so yummy. There's a party. Pretty funny, huh? Let's go get your, can you go up and get socks on? No, I don't. You got tennis. Go get your socks on. I gotta find the checkbook. Yeah. Why? Well, it's okay. You mean Miss Tobin? We'll do it when you get home. You're not missing tennis. It's okay.
Exercise is more important than doing more.
Well, they're both important, but exercise has to happen now. Then work can happen after. So go get your shoes on.
Lyman.
Howdy.
Wow, howdy. So I was reading through the lab, and in part one, I think the sentence that says how many random picked variables we're supposed to have just cuts off mid-sentence.
Okay, it's in the picture.
Oh, okay.
Do you see the picture? Sorry about that. The picture in the columns.
Okay.
Um,
Those each column are randomly picked.
yeah, so let me open up the lab for this week. You're gonna go get your socks on. Go. Hold on, I'm having trouble
You're fine.
finding it here. Here we go. Lab.
Is it the number of slips?
Yeah, number of slips is number of observations.
Oh, so we're supposed to have 9, I think.
So share that screen. Okay. So yeah, down here.
Okay.
So what basically I did 3. So there's 1 and then
Oh.
3 observations, and then you'll do 5, 7, 9, 11, 15, 19, 25.
And so like 9, you'd have 9 observations. For number
Exactly.
19,
Under
you have
9,
19.
Select 9 random numbers. You can use
Okay.
the online generator, but if it's going too slowly, you just want to close your eyes and pick, you can do that too.
Okay, cool.
Does that make
Awesome.
sense?
Yeah.
Okay.
I was confused, but thank you.
Does that
Thank-
help?
Hmm.
Okay. Anything else right now?
I don't think so.
Awesome. Well, I'll be
Thank you.
here. Let me know.
Thanks.